first try to explain what Taiga is and why you might be interested in thinking about this kind of problem and this kind of system. I'll give a kind of overview of the architecture of Taiga that we've designed. I'll talk about why we've designed it that way, and maybe even make some fairly strong claims that other designs are kind of impossible or nonsensical for this definition of the problem. I'll give some usage examples of Taiga and what kinds of privacy you can achieve for multi-party state transitions with Taiga in practice. And finally, I'll list very quickly in 2 slides a bunch of open research directions, less in an attempt to convey in any detail what they are, and more in an attempt to see if anyone else is working on anything similar, and maybe we could collaborate. So first, I just want to give credit. Taiga is part of the Enoma project, and it is built by many people at Helix. Unfortunately, none of them can come today, but they are joining in spirit and perhaps on the live stream. Slightly terrifying. So Joe, Alberto, Julia, Heracles, Simon, and Shuyang all work on Taiga. And I particularly need to give credit to Julia. There's some diagrams in these slides. These diagrams are phenomenal, and they are not made by me. They are made by Julia. So thank you, Julia. So what is Taiga? Taiga is an architecture for private counterparty discovery and private settlement. And in this talk, because I think it's the part that's, at least as far as I can tell, in the discourse a little bit underexplored, I am mostly going to be focusing on private counterparty discovery. What that is, why you might want it, what are the design constraints, and how do we implement it. You might be asking a very reasonable question now that we're talking about what Taiga is, which is, what is counterparty discovery? Sounds like a strange thing. So in order to give a little bit of context on the design problem, I'm going to go back and do a little bit of historical recap of some pretty recent history. So far in the past 10 years or something, a little bit more than 10 years since the introduction of Bitcoin, we've seen many distributed networks focused on what I would call the problem of settlement. Settlement is when you have a state transition, and you know what state transition you want to execute, and you want to execute it on some kind of distributed ledger so that you have double spend prevention, censorship resistance, public verifiability, all of these other nice properties. So all of these protocols are focused on settlement. The first generation, you can call scriptable settlement, Bitcoin, Namecoin, all these weird altcoins. Second generation, programmable settlement, Ethereum, Cosmos, other programmable layer 1s. Then, of course, Zcash pioneered privacy in settlement, so providing you a way to create private transactions so that observers of the blockchain can't see the sender or recipient the amount. And these systems all are focused on settlement. And when you try and add privacy to a settlement layer, you have a specific model of the observer in general. Of course, there are separate questions of network privacy, which is very important. But in terms of engineering the blockchain protocol, you're focused on preventing an observer of the settlement layer, and this is quite easy. Anyone can observe the settlement layer, preventing an observer of the settlement layer to figure out who is sending the transaction, what they're sending, how much they're sending, et cetera. And that's a pretty straightforward, in some sense, problem. But as we see, I think, so far in the evolution of decentralized applications, and if we think about it from a sort of first principles perspective, settlement is just not sufficient. Settlement is what happens when maybe you have, if you're just sending coins, you have one party. But if you're doing some kind of multi-party exchange or multi-party coordination, you have many parties involved, right? And settlement is what happens when those parties already know who they are and what they want. So it's kind of the second step. And there's some prior first step, if you have multiple parties involved, where you figure out who the parties are and what it is that you want to do or coordinate on together, what state transition you want to execute. So we see that many applications need infrastructure for counterparty discovery. If you're building an application where your counterparties, the people who might be involved in some kind of shared state transition or coordination, don't start out knowing each other or don't have some separate private communications channel, they need to find each other. And they probably need to agree on what the state transition is in the first place. So if we think about a marketplace, you might have buyers and sellers. If we think about some kind of quadratic public goods funding, you might have projects, and you might have donors to those projects, and you might have funders, like a sort of government or a protocol who are matching contributions according to the quadratic formula. If you think about DAOs or sort of governance systems, you have different voters. So in all of these cases, there are many different parties, and these parties are they want to be sort of programmatically matched, right? They don't necessarily all know each other. If you're doing a kind of public goods funding, there may be thousands of people. And usually the design intent of these sorts of protocols is to allow these parties to say something about what it is that they want to do together, or who they want to find, or how they want to settle a state transition together, like donors to a public goods funding project and the person who's building the software or the bridge or whatever the public good is in question. They want to find each other on the basis of the shared goal to fund this public good. But then if we think about potentially bringing privacy to such systems, systems are only as private as their weakest link. An adversary is always going to target the weakest link. So if we only solve the problem of privacy for settlement, then the adversary is going to target counterparty discovery. And if you're not really private in the counterparty discovery layer, it doesn't matter as much if you're private in the settlement layer. But let's zoom back one more step and just take a look at how current applications are doing counterparty discovery. There are several different approaches. Maybe the simplest approach, and one that does have advantages, but also really high costs, is to do counterparty discovery on the blockchain. So automated market makers like Uniswap, or variants thereof, do counterparty discovery on the blockchain. An on-chain order book does counterparty discovery on the blockchain. This works, and it provides censorship resistance, but it's really expensive. It's kind of silly because you generally don't need ordering for counterparty discovery. And here you're like paying for this really expensive distributed ordering system that you don't need. And without some other technology involved, of course, these systems don't have any kind of privacy. The second common approach to counterparty discovery is to use a single operator database. So most decentralized exchanges, which deal with programmatic orders, deal with limit orders, deal with NFT, trading, et cetera, follow this model. So we think of OpenSea. OpenSea runs a server. That server stores some orders, and you submit your orders to that server. Then OpenSea figures out like when you can buy or sell or do a bundle trade or whatever, and they submit the transaction to Ethereum, or you do sometimes. But still, all of the orders are stored in that database, and OpenSea, of course, has complete visibility into whatever you're doing. Ditto for 0x relayers. Say for Flashbots. Flashbots operates a private mempool, but not private to them. Roll-up sequencers, single operator database, et cetera, et cetera. So these approaches have an advantage over doing counterparty discovery on the blockchain in that they're much cheaper. You don't need to pay for this really expensive distributed ordering. And you get some privacy. I mean, of course, if you submit things to a single operator database, and some of these databases like OpenSea, 0x are publicly queryable, but some of them are like Flashbots are not. So you get some privacy, but you're not private to the operator of that database, and they can also censor you. Then the third approach, which we haven't seen so much, but a little bit, is a kind of application-specific sovereign chain. So DYDX, for example, the sort of decentralized derivatives exchange, is pursuing this in the Cosmos architecture. And this can provide, you can kind of change your technical layout so that it's a bit cheaper, but it's still posting stuff to the blockchain. It's tons of dev work, and without some other system, you don't have any privacy. So in ANOMA, and just to motivate the problem of Taiga, we've developed a form of generalized counterparty discovery, which is based on a concept called an intent. And an intent is a digital sort of programmatic expression of preferences, which sounds kind of abstract, but it's just like some data. And that data might contain signatures, it might contain proofs, it might contain some clear text, it might contain some encrypted stuff, and it's sent around a peer-to-peer intent gossip network. Then there's a role, so not a specific named entity, but a role we call a solver. And solvers are responsible for finding compatible intents and creating transactions. So this distributed peer-to-peer intent gossip network doesn't provide any ordering. It just provides a way for counterparties to discover each other, and for solvers to figure out, given these many different intents, how they can put them together into a transaction that will satisfy everybody's preferences. Once created, those transactions can then be settled on some settlement layer, aka blockchain. So let's take a simple example here of private bartering. So here we've got 3 different parties, and they want different things. So they have something and they want something else. Want to have an egg, want a star, have a star, want a mushroom, have a mushroom, want an egg. Right? None of them can be matched just as 2. They have to be matched as 3. So in the ANOMA architecture, these parties create intents expressing what they have and what they want. They broadcast those around the peer-to-peer network. Then some solver can realize that they can craft the transaction like the diagram on the right, which will swap all of these assets between these parties, satisfying everyone's intents. So in the simple model, of course, we have no privacy. Intentions are just broadcast around in clear text. Solver creates a transaction. Transaction swaps everybody's assets. So back to what is Taiga. So in Taiga, we want to make this counterparty discovery somehow private. So we want to take this, and we want to add privacy. All right, there's some VP thing. I'll tell you what a VP is later. But just think of it like we want to add some kind of privacy, and you'll notice there are some separate colors on the right-hand diagram which express different kinds of privacy that we can provide, which I'll explain in the next slide. But the kind of goal of Taiga as an architectural design is to take this generalized framework for counterparty discovery and make it as private as possible. So how private can we make it? Well, it turns out, sort of. It's complicated, because privacy in settlement is easy, asterisk. I mean, it's easy thanks to the work done by Zcash and many other parties. But relatively speaking, it's a kind of known problem. Why? Because all of these parties who are participating in the transaction have already agreed on what state transition to effect. So all they need to do kind of is prove to the blockchain that like it was valid, for whatever definition of valid they're using, and maybe there can even be complex properties like function privacy involved in this. All these parties need to do is collectively, someone can create the zero knowledge proof, right? They already know what they want to do, they already know who they are, and they can submit a proof to the blockchain, changing some notes, right? Changing some private state and proving that it was valid. So privacy in settlement is relatively easy, and it's possible to achieve from the perspective of an observer of the blockchain, almost perfect privacy, in the sense that the observer doesn't know the parties, the observer doesn't necessarily know anything about the state transition other than like some state was changed and it was valid, right? So privacy in settlement, fairly straightforward. But privacy in counterparty discovery is not. And the reason for this is that counterparty discovery by nature involves a kind of information sharing. So there are these many different parties, and they have partial state transitions, not full state transitions. They have something they want, say, and some like things that they're willing to do in terms of state transitions that they can affect on the blockchain. And they want to find other parties with compatible preferences with whom they can be matched. But in order to find those parties, they need to reveal something about their preferences. So let's recap the basic form of this generalized counterparty discovery, to which we want to add some kind of privacy. So in this basic form, we have, let's say, Alice and Bob, classic. Alice gives Bob an intent. This intent in the architecture can contain anything, whatever we want to put in there. It could contain data, proofs, etc., right? But this is an off-chain interaction over some kind of gossip network. And Bob needs to be able to test if that intent can be matched with his intent. And if it can, Bob somehow needs to be able to form a valid transaction which will settle the appropriate state change, which satisfies Alice's preferences, which satisfies Bob's preferences, which can be proved to the blockchain as satisfying those preferences, and which affects whatever state change satisfies those preferences and allows the parties to check the new state in the future. Right? So we want to add privacy to this system. But because of this architecture, the way in which we add privacy has to preserve Bob's ability to make this test and construct this transaction. Why? So you could say, like, maybe we construct another sort of system where you kind of submit all of your intents to the blockchain. They're like magically encrypted with everything. And you don't even know whether they've been matched or not. And you could do that. But it's very expensive, because then you're paying to like kind of settle all of these intents which don't actually match. Usually in counterparty discovery, you want to find people, and you only need to settle a state transition if you found people with whom you have compatible preferences. Plus, even if you did this kind of form of like, settle everything, even if it doesn't match, someone would see that their state was changed, right? So there's this trade-off. When you add privacy to counterparty discovery, there's this trade-off between privacy and discoverability. And at least as far as we can figure out, this trade-off is fundamental. It doesn't matter what kind of cryptography you have. So even if you had a kind of like magic FHE version, which somehow is performant, and all you can do with two intents is like test if they can be matched, then, if Alice sends me an intent and I'm Bob, I can just like make up as many imaginary intents as I want to test Alice's intent. So I will still figure out, as long as I have this test, right, I will still figure out the conditions of the compatibility of Alice's intent. Kind of the what, or so to say, of her intent, what her preference is, and what like class or subset of intents would match her intent. So we think this creates boundary conditions on the possible privacy which can be added to this counterparty discovery architecture. Namely, the participants must reveal the information about what would make a counterparty intent a valid match to their intent. But the good news is that they can still hide the who they are. because who they are doesn't have anything to do with what a valid intent would consist of. So let's just look at a very simple example here. So in this, I have a few diagrams like this, and in these diagrams, there are some intents. These intents are boxes, and we're just going to live in abstract land, so these intents are things like A for B and B for A. And then there's a final transaction on the right, and the vertical line is a kind of solving event in the peer-to-peer gossip network, and the arrows are a combination by a solver, right? So in the very simplest case, we have two intents, and we can mask their users, whoever are authoring them. So let's say Alice and Bob. Alice wants to trade A for B, Bob wants to trade B for A. And those two intents can be combined into a final transaction by a solver. And the solver needs to see A for B and B for A, but the solver doesn't need to see Alice or Bob, right? Now, we can do just a little bit better, privacy-wise. So remember, we've just established that we can keep the who private, but the what must be public in this counterparty discovery architecture. So then maybe we can think about, like, what is the degree of kind of privacy loss by making the what public? And this, the sort of degree of privacy loss by making the what public is kind of the degree of uniqueness. Like, this is, again, a kind of abstract way of reasoning about things, but if I create an intent that says, like, do this very specific thing with assets that like only I have for stuff that like only I conceivably want, some observer of that intent can, pretty much infer that it's me, right? But if I create an intent which is much more general, like I want to trade USD for euro or something, there are a lot of people doing that. So it doesn't say much about who I am. So if we want to improve the privacy here, we want to kind of make the what less unique, right? Or we want to combine it with some other whats. And we can do this. So we can do a kind of partial settlement, which is like simplifying or composing intents off the blockchain. Partial settlement involves combining many intents, whats, into a single one. And because we can keep the who private, it doesn't, the who here becomes like some intermediate party. There's no actual party anymore. But as long as the state transition satisfies everyone's intents, it's fine. And here, so let me give a diagram here that explains a little bit about how this might work. So let's say we start off with 4 intents. A for B, B for C, C for D, and D for A. So these intents can be settled in a ring trade, right? Now, let's suppose here that we want to provide as much privacy as possible. And that we know how to like route intents, which is a non-trivial problem that I'm going to skip for now. But here in this model, we have 3 solvers, and these solvers see different things. So the first solver on the upper left sees 2 intents, A for B and B for C. And with only that information, they can combine those intents and make a new intent, which is A for C, right? And if that intent can be matched, then the intent 1 will get C, intent 2 somehow will get A, the person who gives C, right, will get A from intent 1, and everyone's happy. But this is still a partial state transition. Then the third and fourth intents, C for D and D for A, similarly can be combined by another solver who doesn't need to know about the first 2 intents into a composed C for A. Then a third solver can combine these 2 intents, which of course are inverse of each other, into a final transaction. So here, we're no longer dealing with privacy to a single observer. So the model gets more complicated. We're dealing with privacy to multiple observers. And these 3 solvers see different things. So none of them see all of the intents. But the first solver sees 2, the second solver sees 2, and the third solver sees the 2 composite intents. But if we think about this, the third solver is like, if the first 2 intents can be matched kind of early on in the gossip network, the third solver sees only these composite intents from which less information can be inferred about the identity of the original authors. So far, we actually haven't talked about the concrete architecture of Taiga. And this is because I'm a big fan of lazy protocol design. And in lazy protocol design, the first thing you do is try to figure out, for a particular architecture of the system, which protocols are even possible. Like, how much privacy can we achieve in this model, right? And at least our finding so far is that this is the best privacy you can achieve in this model of counterparty discovery, regardless of like what cryptography you're using to instantiate it. Of course, we don't have a formal proof of this, but it seems like pretty intuitive, right? Of course, if you can do something better, please find me. So back to Taiga. I promise I will talk about it eventually. Taiga is an architecture for private counterparty discovery asterisk. So private counterparty discovery as private as possible. And we've just established how possible privacy is in counterparty discovery. So Taiga just provides these privacy properties. In using Taiga for counterparty discovery, identities, i.e. who is creating the state transition, are private. But assets, amounts, and constraints, what, are public to observers in the gossip network, not necessarily observers of the settlement layer. Then from the settlement perspective, so the blockchain, identities and assets, amounts, constraints are private. So fully private settlement, partially private counterparty discovery. How do we do this? Well, honestly, in ways that you're probably pretty familiar with. We use zero-knowledge proofs for data privacy, similar kind of note model to Zcash, Zexe. Create a note commit, spend a note, prove in zero knowledge that your action is valid. We use zero-knowledge proofs for function privacy, so observers of the settlement layer know, and observers of like partially matched transactions know whether a validity predicate allows a state transition, but they don't know the function content. The validity predicate, I'll talk about what validity predicates are in just a slide. And then we have a kind of proof segmentation for these phases of counterparty discovery that I outlined in the diagram, which allows participants who are authoring intents to keep private whatever you can keep private, and allows intermediate nodes in the gossip network to do this kind of partial solving and intent composition. So let's go back to the example of private bartering from before. What are properties that we need for private bartering? Private bartering must be atomic. So if 3 parties are swapping stars, eggs, and mushrooms, we don't want to have them swapped like in 2 separate transactions, right? Because then, maybe one transaction goes through, the other doesn't. Maybe it's a free option, right? We want private bartering to be atomic. Private bartering also must be authorized. Well, duh. If we want to send these users assets around, they better have approved that we're doing that, and they'd better be happy with the assets that they're getting in return. So in the Taiga architecture, we have a concept called a validity predicate. And a validity predicate, there are 2 kinds of validity predicates in Taiga. There are user validity predicates and there are token validity predicates. And user validity predicates are what users use to encode their preferences and their intents. They're circuits, so they're programmatic. Users can encode whatever kinds of authorization they would like, such as a signature or multi-sigs or different limits. And token validity predicates govern the relations of the tokens. So like stars, want to be conserved. Maybe stars are non-fungible, they are unique, and if you burn a star, you can mint the exact same star, but you can't do anything else, right? So what is a VP, or validity predicate? A VP is just user-defined code that takes ephemeral data, such as intents, and authorizes transactions. So Taiga, of course, provides privacy in the sense that the who is hidden. Those are the black cloaks on the right there. And the what is hidden in settlement, but partially visible to different observers in counterparty discovery. So those are the star, the egg, and the mushroom, with somewhat opaque, but not fully opaque bags around them. And Taiga also provides verifiability of this authorization, so that from the perspective of the settlement layer, you see, some parties engaged in an interaction and they changed around some state, and you don't see any of what state was changed or who those parties are, but you can check that all of the validity predicates, whatever they were, did in fact authorize these state transitions, which did in fact occur. So you might ask, how is this, sounds like kind of like Zexe, right? In a sense, it is. Taiga, Zexe, and Zexe all have pretty similar properties. They all have data privacy. They all have function privacy. But at least for the versions of Zexe and Zexe that I'm aware of, they have different implementation architectures. Because in Taiga, we're very focused on this counterparty discovery problem. So Zexe and I think Zexe are architected around birth and death predicates, kind of have implicit signature checks. In Taiga, we use a different segmentation, so we split things into user validity predicates and token validity predicates, which in our model allows for this separation of user and application authorization. It means that user VPs can do programmable authorizations. They can have like spending limits per day. They can have state, right? Just represented as an NFT in the circuit. And Taiga also accounts for this off-chain partial settlement, right? So you only really want to post your transaction to the blockchain when it balances and you've agreed on it, and even it's like, maximally compressed. You could always take 2 valid transactions and make another valid transaction, and maybe then it's cheaper to settle. Only order when you need to. So Taiga is similar to Zexe in terms of broad properties, but has a different kind of implementation architecture and different segmentation of proofs. So let's go back a step. I just gave examples of bartering. That seems kind of specific. But in Taiga, bartering is generalized. And generalized bartering is just like multi-party private state transitions, with this kind of intent transaction separation. And this intent transaction separation, when you think about it, is really just the difference between whether or not the ordering happens on the blockchain and whether or not the transaction is fully balanced. So when you do this kind of intent composition or reduction, you're doing a sort of, not exactly ordering, but like atomic combining, right, off the blockchain. And you can do that as long as you want, and post the final thing to the blockchain and then order it with respect to all of the other transactions, only when it's balanced and when you want to post it. Which means the Taiga can be used, in this general sense, for a lot of different things. It can be used for private multi-party bartering, like I gave an example of. So intents, which have arbitrary constraints, let's say you want to, I know it's overblown, but you want to atomically purchase hotel, train, and festival tickets. I really do have friends who've occasionally failed to atomically purchase these things. And you want to do so in private. You could use Taiga for that. Let's say you want to do private, multi-party, multivariate, quadratic public goods funding. Too many acronyms. First, what do I mean by private, multi-party, multivariate, quadratic public goods funding? Particularly the multivariate part. So public goods are non-linear. And many public goods you might want to fund can only really be produced if there's a certain amount of resources dedicated to them. Maybe software is kind of an easy public good, right? You can just sort of donate to the person maintaining software, but still there's still non-linearities, right? They need enough per month to pay for their apartment and pay for their food. And if people don't donate in total that amount, maybe they have to work another job, right? The problem gets much more serious if you're trying to fund more difficult public goods, especially those with physical exclusivity, such as a bridge or something in the physical world. And in those cases, not only do you have thresholds in terms of what amount of funding needs to be contributed to fund specific public goods, but you also have exclusivity in physical space between different public goods. You cannot fund 2 bridge proposals to build a bridge with different properties at the same location. Doesn't make sense, right? So you need a way to express these kinds of constraints in a set of public goods that you're wanting to fund collectively or as a community. And in Taiga, you can express these constraints as a part of the intents. So contributors, there are 3 classes of entities in this quadratic public goods funding model. Contributors who want to donate to specific public goods, projects who are making proposals, and those proposals have constraints, such as requiring occupation of particular physical space for a bridge, such as requiring a certain amount of funds if they're going to produce the public good at all, right? And those projects, or the people who are proposing projects, make proposals. They author intents, just as the contributors author intents. Then the funder might be a government, might be the blockchain printing inflation, might be some other community fund. In the quadratic model, the funder matches in terms of a quadratic formula such that more contributors have a sublinear return to amount of funding donated to a particular project. And this, in the Taiga architecture, all of this matching happens off the blockchain. And then one single transaction, perhaps by the funder acting as solver or by some other solver, can be created to settle it to the blockchain. And you can get a nice kind of privacy here because many of these things can be combined. So if we think about donations to several different projects, you still have to reveal the number of people donating, but you can hide their identities, right? If we think about projects making proposals, I mean, maybe you don't necessarily always want privacy there. You might want some things to be revealed. Think about a funder matching contributions. You can get privacy for the who in this kind of counterparty discovery phase, and then in settlement, you can get privacy for everything and reveal specific parts. The third usage example here is a kind of private organization. DAOs are very popular right now, but they tend to be eaten up by bike shedding, and most organizations in the real world operate with not necessarily full privacy, but at least selective disclosure. And I think this is pretty essential. If you don't have selective disclosure for your organization and how you're making decisions, it's really easy for anyone in the world to cherry pick data, kind of misrepresent what's going on, just sort of denial of service attack your organization. We see this on, for example, Discord chats, which are not really set up to be well administrable, right? And we see this with many kinds of many kinds of decentralized organizations. So I think adding privacy might be compelling here. And with Taiga, you can get a kind of programmatic multi-signature or other kinds of rules around what parties have to agree and in what way they have to agree to spend funding or to take action as an organization. And because of this programmatic architecture, you can program whatever rules you want in, and you can do all of the kind of gossip of these votes around off the blockchain and only send a transaction once you want to actually enact some kind of state transition that all of the members of the organization have agreed to in a way that, according to the organization's rules, constitutes a valid action. So If you want to learn more about Taiga, you can find the current state on GitHub. It's open source at github.com/anoma/taiga. I would say that this is like a spec and early prototype. Please don't use it in production yet. You may need to explore some Git branches to find this, but we have implementations that we're trying to benchmark for both Plonk up-ish, Plonks, there are many Plonks. It's difficult to describe exactly their differences these days, but we have R and ZK Garage's Plonk, which is like Plonk plus plookup plus some other extensions now. And we also have an implementation for Halo 2, so thank you, of course, ECC for Halo 2. You can find those. You can find a few simple example validity predicates, architecture diagrams, specifications, documentation. You can create proofs. It's still a bit slow, early stage, but feedback is very welcome. And we're hoping to be one of the users. I think we'll end up going with the Halo 2 variant, so we're hoping to be one of the users of Halo 2 as well. And we have a few outstanding research directions. Privacy I really think that I hope that Zcash or other projects can really execute on go-to-market for private transfers, because I feel like in the world, outside this room and these people who know about these things, that still isn't prevalent. And I think that is by far the easiest go-to-market use case for privacy that would have a really public benefit to society. In order to make other kinds of applications private, there's so many UX trade-offs that I think we really need to do a lot. Still, we need to do a lot of protocol design work, see how we can combine different cryptographic primitives, see what can be brought into play to kind of enable a balance of, a user experience that is reasonable, that doesn't make too many trade-offs, and that without users understanding all of the choices of curve selection and architecture of the cryptography allows users to engage with each other or do whatever the application is doing pretty safely. The only application which has done this in practice, as far as I can see, is Signal. I can talk to my artist friends in Berlin who hate surveillance capitalism but do not understand cryptography and, kind of explain how Signal works. And you can use Signal safely without understanding double ratchet, right? And say a Zcash mobile wallet has a kind of similar, if the UX is architected really well, users can be protected. But for other kinds of more complex applications, I think we'll need some more cryptographic primitives involved. So in Taiga, part of our research is integrating more cryptography and kind of connecting it, or so to speak, to zero-knowledge proofs in a way that allows the two to work synergistically and cover sort of different parts of different applications privately by working together. So there are two primary research directions there. The first is integration of Fairvio. Fairvio is a distributed key generation and threshold encryption-decryption system, which can be used for front-running protection, for example, but it can also be used for, say, temporary privacy. And this is very useful for things like private bridges, useful for sealed bid auctions where you want to reveal after a period of time, stuff like this. And we're trying to integrate this with Taiga so that you can prove in zero knowledge that you've encrypted specific data to the Fairvio threshold key, and maybe we can even do a kind of threshold re-encryption to some specific party in a note. In the other direction. You can find more info on that on ICR. Then we're also, very early stage, but I think there's a compelling case that an integration of some FHE with zero-knowledge proofs where you do only the little bits of your application that require shared multi-party private state in FHE, because it's very slow, and you use zero-knowledge proofs for everything else, that might be able to enable some things that you otherwise just can't get because you can't get multi-party private state with CKPs. So we're investigating that. But the other research direction, which I think is really important and still kind of underexplored, is programming model and compiler stack for private applications. Private applications are hard. So if we go back to Counterparty discovery, there's this state. And really, in some sense, the way you get privacy with zero-knowledge proofs is by distributing your state. So the users have their own state, and then they're making proofs about how they compose changes to that state and proving that it's valid according to their authorization rules, right? This is a very tricky model. So far, blockchains mostly worked like a sort of virtual cloud, right? And in the cloud architecture, you have a client, you have a server, and the blockchain kind of just replaced the server, and you make queries to the server, and you submit transactions to the server, and it's a very straightforward architecture because all of the state lives in one place on the server. And if you use Ethereum, all of your state lives on Ethereum, or you're using an indexer, but it's just a kind of derivative of the same thing, right? But if you genuinely want private applications using zero-knowledge proofs, you need to distribute your state. And I think in order to write safe private applications, developers who are not necessarily going to understand all of the cryptography and can't be expected to need clear abstractions that capture the kind of privacy properties without without requiring understanding of specific cryptographic choices, or at least outsourcing some of those choices to orthogonal configurations or even to compiler, eventually like compiler optimizations. So we're doing a little bit of work in this direction. One thing we're developing is a kind of polynomial IR called Vampire. So if you think about the architecture of traditional compiler stacks, often you have, I guess the best example here is something like LLVM. So we have lower level architectures, x86, RISC, et cetera, which are register machines. And they are specific register machines with specific numbers of registers. And that, it's kind of annoying to like target all of those things, right? So many brilliant compiler engineers have built LLVM, which is a kind of abstract register machine, which has an infinite number of registers. And the LLVM translation passes convert infinite register code to finite register code. So similarly, we think that it makes sense for this kind of layer to exist in the zero-knowledge proof system compiler stack. And most zero-knowledge proof systems work with some representation of polynomials, but they have specific constraints on those polynomials. And maybe they have their circuits with specific gate arities, et cetera. Or they have different costs for addition or multiplication or lookup gates or other operations. So we're building a kind of polynomial IR roughly analogous to LLVM called Vampire. Vampire has sort of arbitrary polynomials. They're just like polynomials. And they can have any degree you want, et cetera. And then the Vampire compilation turn that into different proof systems, like Plonk-up-ish or Halo 2. We're working on some HE backends. And hopefully we'll be able to automate some of those transformations, or at least simplify the choices programmers have to reason about and allow proof systems to be improved in parallel. Then on top of Vampire, or on top of a polynomial layer, we think developers will need higher level abstractions or higher level programming languages. And so far there seem to be kind of three approaches to this. So one thing you can do is build a sort of domain-specific language on top of polynomials or on top of circuits. That has the advantage of being closer to the virtual hardware, or so to speak, and relatively straightforward. But the disadvantage of having semantics that are kind of tied to polynomials, hard for developers to reason about, and crucially different than the public parts of their application. And in applications where there's some public state transitions, some private state transitions, we think it will be difficult for developers to reason about those applications and to make them safe if they always have to be doing these semantic conversions and data conversions, because those conversions are easily a place where bugs can be introduced, or you can make data public that you didn't want to make public, et cetera. So DSLs from that perspective have some disadvantages. The second approach is a kind of intermediate instruction set architecture. So the fine folks at RISC-0 actually have developed a Stark for RISC-V, which is stunning. I didn't think that would happen a year ago, and happily I was wrong. That has the advantage of being a standard compiler target. It's something you can write a higher level language with semantics that developers will be used to, and that can be basically identical to the transparent execution semantics. But it has the disadvantage that you've introduced this instruction set architecture in the middle of your circuit compilation path, which really wasn't designed for circuits, and which is kind of RISC-V and x86 are designed based on, as far as I understand it, the physical efficiency of implementing certain things in memory fetches and cache architectures on physical CPUs in manufacturing processes. And these are not the same optimization criteria that you have in circuits. So you're going to pay a cost for this intermediate instruction set architecture. And it's also not necessarily RISC-V code, x86 code is built in this Turing machine model where you sort of run forever and you're taking some user input and you have all these other interactivity constraints. And when you're doing private state transitions, you don't want to run a non-terminating computation. So there's more power here than you need. And the third approach, which at least we're investigating because we have a higher level language based on the lambda calculus, is with some stuff from a paper called Compiling to Categories, directly translating lambda calculus to polynomials, which is surprisingly possible, although only for a terminating variant. So we're trying to figure out which of these approaches have which performance characteristics, and working on some benchmarks for example applications. And I cite this here because we'd really love to collaborate with anybody who's also interested in these questions. And maybe these are many, many different compiler directions. Maybe we can divide labor efficiently. So finally, hopefully I still have 3 minutes for questions. I want to say thank you. Anoma loves Zcash. We wouldn't be here without Zcash. And we are really interested in helping and in finding the best way to do that. One thing we're interested in is potentially building a Zcash bridge After some excellent talks on Frost yesterday, I actually wrote up a proposal for a pretty sort of non-custodial trust minimized bridge. You can find it on the Zcash community forums, and I'd really love feedback, and I'd like to know what the Zcash community thinks of a bridge and thinks of this kind of, for example, in this proposal, you can use Zec for all of your fees, so you don't need to acquire any other assets. But yeah, I'd like to know what kind of criteria people have for this sort of system, whether it would be welcome, useful. And you can find me on Twitter, or of course here, and find us similarly on Twitter. Thank you very much.
So you did such a good job explaining that there was no questions. So we'll get on time. We started you a little late, so we'll get back on time. And thank you again, Christopher. That was awesome.